In this lecture, we will talk about the vapor pressure of liquid solutions. We will be considering two different types of liquid solutions. Number one, when we have a liquid with another liquid, and number two, when we will have a solid in a liquid. Now, whether we take a liquid in a liquid or we take a solid in a liquid, both the solutions will be liquid solutions because the major component solvent will be a liquid. Okay, so let's take up these two one by one. And before that, let me just tell you what is vapor pressure. How do we define vapor pressure? So what is vapor pressure? For that, just consider a system in which there is a liquid taken and the liquid is volatile. So it is a volatile liquid. Volatile means it can evaporate. So it will start evaporating after some time. So you will have evaporation, and after some time the reverse process, which is condensation, will also start taking place. So there will be two processes taking place in this container, and when the rate of these two processes will exactly be the same, the system will attain dynamic equilibrium. Now, when the system attains dynamic equilibrium, at that point of time, whatever pressure these vapors are going to apply, okay, this pressure is referred to as the vapor pressure. Okay, so this pressure is referred to as the vapor pressure. So how do we define what is vapor pressure? You can say that it is the pressure exerted by the vapors. It is the pressure exerted by the vapors of a liquid. Okay, it is the pressure exerted by the vapors of a liquid on the liquid surface, at equilibrium in a closed container. So this is how we define vapor pressure. And now let's talk about the two systems, as I mentioned, the liquid and the solid-liquid system. So we are considering the first system. The first system was a liquid solution. So both the components, the solute and the solvent, okay, both are considered here as liquids. And one more thing, that both of the components, that is the solute and the solvent, they are volatile. So they are volatile, that means they can evaporate. Volatile means they can evaporate. Okay, so we have a system of two liquids, the solute and the solvent, and both are volatile and can evaporate. So you can imagine the system to be like this. So in a closed container at a particular constant temperature, I have taken two liquids here. So one is liquid 1 and second is, let's say, liquid number 2. Now how much of liquid 1 and 2 are there in the containers, that I am considering in terms of their mole fraction. So let's say chi 1 is the mole fraction of liquid 1 and chi 2 is the mole fraction of liquid 2. And now as they are volatile, they start to evaporate. When they start to evaporate, they start exerting some pressure also. So let's say P1 is the pressure exerted by chi 1 and P2 is the pressure exerted by the component number 2. So P1, P2 are the pressures exerted by the two components. Also consider Y1 and Y2 also in the vapor phase. Now what is this Y1 and Y2 here? Y1 and Y2 are the mole fractions. They are also the mole fractions of the same two liquids, but these are the mole fractions in the vapor phase. Just like we have chi 1, chi 2. Chi 1, chi 2 are the mole fractions in the liquid state. So we can have chi1, chi2 mole fractions in the liquid phase and y1, y2 mole fractions in the vapor state. Now for such a system of two volatile liquids, Rawls gave a law and gave a quantitative relationship also, which is known as the Rawls Law. So let's see what is the Rawls Law. Now as per the Rawls Law, for a system of two volatile components, okay, like we have taken liquid 1 and liquid 2. So for a system of two volatile liquids, as per the Rawls law, the partial pressure, which means the pressure exerted by a particular component, the partial pressure of each component, of the solution is directly proportional to its mole fraction in the solution. So as per the Rawls law, the partial pressure of each component of the solution is directly proportional to its mole fraction in the solution. This means that P1 is proportional to chi1 and P2 is proportional to chi2. So what is P1 and P2? P1 and P2 are the partial pressures. This is the partial pressure of component 1 and this is the partial pressure of component 2, and chi1, chi2 are the mole fractions, mole fraction of component 1 and mole fraction of component 2 in the liquid phase. Now when we replace these proportionalities and put constants, these equations, they change to P1 is equals to P1 naught into chi1 and P2 is equals to P2 naught into chi2. These are the you can say mathematical or the quantitative relationships between the partial pressures and the mole fractions as per the Rawls law. Now what is P1 naught and P2 naught here? Let me tell you that. Now what is P1 naught? P1 naught is the vapor pressure of the pure component number 1. Pure component, we have denoted it as 1. So this is the vapor pressure of the pure component 1. And likewise P2 naught also, if you mention what is P2 naught, P2 naught is also the vapor pressure of the pure component, right? So there is a difference between P1 naught and P1, P2 naught and P2. P1 naught, P2 naught are the vapor pressures of the pure components, which means when they are present alone in the system. But P1 and P2, so let me just mention here below P2 that P1 and P2, what are they? These are the partial pressures of the two components 1 and 2, and partial pressure is the pressure exerted by a component in the presence of the other, because in the system we have 1 and 2 both together. So in the presence of 1, the pressure exerted by 2 is its partial pressure. Likewise in the presence of 2, the pressure exerted by 1 is its partial pressure. So I'm repeating the statement of the Rawls law one more time. The partial pressure of each component of the solution is directly proportional to its mole fraction. Now, applying the Dalton's law of partial pressure. You've studied this in class 11th. So, as per the Dalton's law of partial pressures, PT should be equal to P1 plus P2. And what is PT here? PT is the total pressure. PT represents the total pressure of the system. It will be equal to the sum of the partial pressures of the two components. So PT is equals to P1 plus P2. Now let's use the Rawls law. So PT is equals to P1. And what is P1 as per the Rawls law? It is P1 naught into chi1 plus P2. P2 is equals to what? P2 naught into chi2. And now we'll be using one more information. If you remember that the sum of the mole fractions of all the components taken together in a system is equals to 1. As we have two components, so chi1 plus chi2 will be equal to 1. So if I replace chi1, okay, so what will be chi1 from here? Chi1 will be 1 minus chi2. So I'm going to do that. I will be replacing chi1 in this expression now. So p1 naught into chi1 can be written as 1 minus chi2 plus the same thing, that is p2 naught into chi2. Let's multiply. So p1 naught minus p1 naught into chi2 plus p2 naught into chi2, and I have rearranged it further. Then p1 naught as it is, and let's take chi2 common from both these terms. So from the second and the third term, if I take chi2 common, what will I be left with here is p2 naught minus p1 naught into chi2. So this is a relationship. This is a relationship that we have derived for the total pressure, expression for the total pressure of a solution where we have two components, 1 and 2, and P1 naught and P2 naught. What are these? These are the vapor pressures of the pure components. And what is chi2? Chi2 is the mole fraction of component 2 in the solution. Now using this relationship, if we plot a curve between vapor pressure, let's take vapor pressure on the y-axis and mole fraction chi2 on the x-axis. As you know, the mole fraction minimum can be 0 and maximum it can be 1. Okay, so let's see when chi2 varies from 0 to 1, how will the total pressure vary. Now if you substitute the value of chi2 equals to 0, so this is the point where chi2 is 0. Putting chi2 equals to 0 here, I'll be left with only P1 naught. So when the value of chi2 is 0, total pressure is equals to P1 naught. Let's take this as P1 naught. So I am considering that this point here represents P1 naught, which is the vapor pressure of the pure component 1. Okay. Now as chi2 increases from 0 to 1, okay, as you can see from the expression, when you increase the value of chi2, what should happen? The value of P total should change. Okay, and now if I consider the maximum value of chi2, which is equals to 1. So considering the maximum value of chi2, which is 1 here, if you put that equals to 1, P1 naught will get cancelled and you'll be left with only P2 naught. Okay, so as you reach chi2 equals to 1, the total pressure will be equal to P2 naught. So let's imagine somewhere here, the value of P2 naught. So let's consider this point and let's take this as the value of P2 naught. So that means when chi2 varies from 0 to 1, the total pressure varies from P1 naught to P2 naught. So this is the variation of P total, which is equal to P1 plus P2. Now we can even consider the variation of the partial pressures of the two components. So if you remember, as per the Rawls law, P1 was equal to P1 naught into chi1 and P2 was equal to P2 naught into chi2. So let's first try to plot the curve for P2. Okay, we are trying to plot the curve for P2 first. So again, when the value of chi2 equals to 0, if you put chi2 equals to 0 in this expression, so when chi2 is 0, P2 is 0. So the graph starts from the origin right here. Now as the value of chi2 will increase, as P2 and chi2 are directly proportional, as chi2 increases, okay, as chi2 increases, P2 also increases. So the pressure is going to increase. It will start to increase like this. And now finally, when the value of chi2 will be equals to 1, when you put the value of chi2 equals to 1, P2 becomes equal to P2 naught. So when chi2 will be equals to 1, which is this point, P2 will be equal to P2 naught. So this is how the partial pressure of component 2, P2, which is equal to P2 naught into chi2 is going to vary. And likewise, as we know that the sum of the mole fractions is always equal to 1, so how will chi1 vary at the same time? When chi2 is equals to 0, chi1 should be equal to 1, and as chi2 approaches 1, chi1 should become 0. So now at this point of time, the value of chi1 is 1. So if I put the value of chi1 equals to 1 here, if chi1 is 1, P1 is equals to P1 naught, right? P1 will be P1 naught. So the graph is going to start from this point now, P1 naught. Now as chi1 from 1 to 0 is decreasing. So when chi1 will decrease, P1 is also going to decrease. So the graph is going to come down like this. Okay. And finally, when chi1 will be equal to 0 exactly. So when you put chi1 equals to 0, P1 becomes 0. So the graph is going to end at 0. And so like this, you can show the variation of P1. So this represents the variation of partial pressure of component 1 P1, which is equal to P1 naught into chi1. Okay. Now here there's an assumption that component 2 is more volatile. It is more volatile than component 1. It's because I have taken P2 naught higher than P1 naught. So this shows that the vapor pressure, by the pure component 2 is more. So that means component 2 is more volatile than component 1. This is just an assumption. You can take it the other way around also. Now if you are asked to find out the composition of the vapor phase, okay, composition of the vapor phase, that will be calculated in terms of y1 and y2. I told you what is y1 and y2. Y1 and y2 are the mole fractions. They are the mole fractions of the two components in the vapor phase. Now to calculate the value of y1 and y2, you will have to use the relationship that P1 is proportional to y1 and P2 is proportional to y2. When you replace the proportionality signs, you get P1 equals to P total into y1 and P2 equals to P total into y2. Now let's consider the second system where we have a solid in a liquid. Okay, so the solute is a solid and the solvent is liquid. The solute, which is a solid, is non-volatile in this case, whereas the solvent is still volatile. So the solvent can evaporate, but the solute cannot evaporate. Now let's see what will happen to the vapor pressure of such a system. Okay, to understand this, first of all, imagine the situation. In this container, let's say we just take the solvent which is volatile and is capable of evaporating. So what will happen? The solvent is going to evaporate. All right, and when it will evaporate, it will exert some pressure, and let's say the pressure exerted by the solvent is P1 naught, because we have the solvent alone here, so we have to denote it by P1 naught. So the vapor pressure of the pure solvent P1 naught here, and because we only have the solvent, so I'm just showing these circles to represent the solvent particles. So these are the solvent particles. The surface is covered by only the solvent particles. Now to this solvent, if you if you add some solute, okay, if you add some solute, what will it be converted into? It will be converted into a solution. So now finally we add a solute, and the solute we have taken is non-volatile and it is converted into a solution. So what we have right now here in this container is the solution which contains both the solute and the solvent. So now this solution has both. So now the surface won't be covered by only the solvent particles, but some of the surface is also going to be covered by the solute particles. These dark circles, right, are representing the solute particles. Okay, so this is a solution. It contains both solvent as well as the solute. Now what happens? The solute is not volatile, but the solvent is still volatile, so the solvent will evaporate. But as you see that some of the surface is now covered by the solute particles which are not volatile, the tendency of the solvent to evaporate decreases. So I'm mentioning the important point here, that the tendency of solvent to evaporate decreases. Okay, the tendency of the solvent to evaporate decreases, and that's because some of the surface is also covered by the solute particles. Now certainly there will be some pressure exerted. Now let's say that pressure exerted is represented by P, and now what is P? P is the vapor pressure of this solution. P is the vapor pressure of this solution, and I can denote it by P1 also. Why P1? Because whatever the vapor pressure of the solution is, it's actually because of the solvent, because solute is non-volatile. right? So this is the pressure exerted by the solvent in the presence of the non-volatile solute. So let's take it as P1. So what is P1? P1 is the vapor pressure of the solution. So I'm mentioning here P1 naught is what? P1 naught is the vapor pressure of the pure solvent, whereas what is P1? P1 is the vapor pressure of the solution that we have formed. And it is quite obvious that if we draw a comparison between P1 naught and P1, P1 will be less than P1 naught. As we saw here, that lesser solvent particles will now be going into the vapor phase because some of the surface is covered by the solute which is not volatile. So P1 will be less as compared to P1 naught. So what you see here is, you see a decrease in vapor pressure. What is observed here is decrease in vapor pressure. So whenever a non-volatile solute is added to a solvent, the vapor pressure of the solution will get decreased. Okay, and now here if we plot a curve between the vapor pressure and mole fraction, so let's say this is vapor pressure and this is the mole fraction. Now this time we only can take the mole fraction of the solvent because the solvent is only volatile, solute is non-volatile. The solvent was 1, it was represented as 1. So P1 as per the Rawls law is equals to P1 naught into chi1, whereas P2 in this case will be 0. Why will be P2 0? Because the solute is not volatile. 2 is the solute, okay? I am considering 2 as the solute, 1 as the solvent. So because the solute is not volatile, so P2 is equals to 0. And what is P1? P1 is P1 naught into chi1. So for this case, if I will have to take the value of P total, which is actually equal to P1 plus P2, what will it be equal to? Considering P2 equals to 0, P total will be equal to only P1. So what is P total equals to? P1 naught into chi1. So we have reduced down to only this. Why? Because the solute is not volatile. So if you plot a curve of P total, it will be equal to P1 naught into chi1. So when you put chi1 equals to 0 here, Pt will be 0. So you start from here. And as chi1 will increase, Pt will also increase, and when chi1 will be equal to 1, Pt will be P1 naught. So let's say somewhere here, this represents P1 naught. So this is the variation of P total you may say, or P1 you may say, which is equal to P1 naught into chi1. So I hope you've understood that when one of the component in the solution is not volatile, like in our case P2 is the pressure exerted by the solute, which will be 0 only because the solute was not volatile. So P total is reduced down to only the vapor pressure of the solvent alone, and so Pt is equals to P1 naught into chi1, and this is the variation of total pressure, or P1 you may say. Now we will see how the Rawls law as a special case of Henry's law. Rawls law is actually a special case of Henry's law. Alright, so we have already talked about Henry's law, and if you remember, the Henry's law was for a system of a gas dissolved in a liquid, and as per the Henry's law, P is equals to KH into chi. And now if you consider the Rawls law, as per the Rawls law, which is for a liquid in another liquid, the partial pressures of the components, they are equal to P naught into chi. So P is equals to P naught into chi even for the Rawls law. Now let's say this is equation number 1 as per the Henry's law, and this is equation number 2 as per the Rawls law. But you know what is common? As per both the laws, the partial pressures, the partial pressure of the gas, okay, this was the partial pressure of the gas, and this is representing the partial pressure of any one of the component, okay. So the partial pressure of the gas or the partial pressure of the component are proportional to their mole fractions. Chi here is what? Chi is the mole fraction of the gas, and chi here is the mole fraction of the component in the solution, and KH and P naught, they are constants. So what we see is that as per both the laws, I'm writing it here. As per both the laws, the partial pressure of the gas or the volatile component are directly proportional to their mole fractions in the solution. Okay, so as per both the laws, the partial pressure of the gas or the volatile component are directly proportional to their mole fractions in the solution. Okay, so the two are conveying the same information. And when the value of Kh, the Henry's law constant, becomes equal to P naught. What was Kh? Kh was the Henry's law constant. And what is P naught? P naught is the vapor pressure of the pure component. Okay, so when Kh, the constant Kh, becomes equal to P naught, then the two laws are exactly the same, or you can say then the Rawls law is same as the Henry's law. So the Rawls law is nothing but it is a special case of the Henry's law. In both the laws, the partial pressures are directly proportional to the mole fractions of the components in the solution, and they are related to each other through constants Kh and P naught. And when these two constants are exactly the same, then the two laws also become exactly the same.